Well, welcome everybody. Thank you for coming, all of you. It is a great pleasure to me to introduce this first block of our group actions in differential geometry session. So today we will have 6 talks, and the first one is the Marco Radeschi talk. And thank you. I would like to thank all the speakers because of these great talks. So today our first speaker is Marco, and he's from University of Notre Dame, and he'll speak about invariant theory without groups. Thank you, Marco.
Thank you very much. So first of all, thank you very much for the invitation. And as the first speaker, I would like to thank the organizers also for organizing and setting up this special session. I'm sure it will be incredibly interesting already seeing the list of names of people that will speak. So the title of the special session is a group action in differential geometry, and what I'm going to do in my talk is I'm going to talk about a recent development of with a few co-authors on a theory that tries to remove group actions from differential geometry. So I hope you will forgive me for that. So let me start by recalling a little bit of invariant theory. Oh, how did this get in here? Oh, well, let's actually get to our talk. So let me recall a little bit of invariant theory. By the way, most of what I'm going to talk about is joined with Ricardo Mendes from University of Oklahoma. And again, going back to invariant theory, I'm going to start with a very special situation where we have a vector space V, and we have mostly will be a compact group acting by isometries via linear isometries. And whenever you are in this situation, well, it makes sense to discuss about the ring of polynomials that are invariant under the G action. And it will be more convenient to think of them as just the polynomials that are constant along the orbits of the group. And well, whenever we are in this situation, of course, it gets a little bit more general, but I will specialize to this. Then the point of invariant theory, of usual invariant theory, is to study a representation, the geometry of the representation by studying the algebraic property of the ring of invariant polynomials. Now, a small and the kind of rather silly remark is the following, that as a matter of fact, if you have two different representations that are orbit equivalent, namely they have the same orbit, then in fact, the polynomials that are constant on the orbit of one action, they're constant on the orbit of the other, and vice versa. So the two rings are in fact the same. So this suggests already the idea that when you look at the polynomial of the algebra of invariant polynomials, you're not really studying the action itself, but rather the decomposition into orbits that it creates. And this kind of already goes in the direction that maybe it's, if you study this, it's not really the group that you are studying, but something that is slightly different. And in fact, the point here is we try to remove the group from the picture. So, and we do it in the following way, by observing that, again, if you have an orthogonal representation of a closed group, then in fact, the group acts on the unit sphere. And you have a few things. First of all, the quotient of the action, the orbit space, is a Hausdorff metric space where the distance function is between 2 points is simply the distance between the two corresponding orbits. This in the case where the action is orthogonal, this does really induce a distance function on x. And the second property is that the canonical projection map that takes every point to its own orbit. This map here has smooth fibers, clearly they are the orbits, and they are equidistant. And so what you can do is you can try to remove the group by replacing the group action with something that has these two properties, and we call such object a spherical manifold submetry. So once again, a spherical manifold submetry is simply a map from a round sphere down to a Hausdorff metric space whose fibers are smooth and equidistant. The manifold has to do with the smoothness of the fiber. Submetry essentially it has to do with the equidistance of fibers. I will refer to these as SMS or just submetries, just to avoid repeating myself too much. And you can think essentially of these objects here as orthogonal representations without groups in some sense. And okay, here the point is that they don't appear just like this. They really, these manifold submetries generalize a bunch of well-known facts, well-known structures, as I said, orthogonal representations, but also Riemannian submersions, singular Riemannian foliations, and also families of isoparametric submanifolds. These objects have a long history, and they have been studying, and the classification is almost complete for these objects. Not really fully, but almost complete. So the point is that all these objects have this common property of being representable as a spherical manifold submetry. And another property of these spherical manifold submetries is that they represent the infinitesimal approximation of a general manifold submetry. And a manifold submetry is essentially the same thing. The only difference from a spherical manifold submetry is that we do not require now M to be a sphere, but it could be just a general Riemannian manifold. Again, if you linearize this concept of manifold submetry, you get into a manifold submetry from a sphere. And finally, well, I don't want you to think about too much about this, but I just still wanted to add it in here. Spherical manifold submetry are somehow the universal, are the biggest object you can find whenever you study manifold submetries from manifolds that have sectional curvature larger than or equal to 1. So in some sense, the largest you can get is in the case of a spherical manifold submetry. As a matter of fact, for me, these 2 points are somehow conceptually the most important things that somehow make spherical manifold submetries interesting to study. And okay, so as I was saying, if we think of spherical manifold submetries as representations without groups, then we can do an invariant theory without groups in a pretty straightforward way. We can just like in the homogeneous setting, we can define a ring of basic polynomials. That just means polynomials that are constant along the fibers of the manifold submetry. And the goal of this, if you want the invariant theory without groups, would be to study and understand the geometry of the submetry and of the quotient space via understanding the algebraic properties of the of the ring, of the corresponding ring. And something that, well, essentially, I will tell you what the result is, but first of all, I need to define this concept of Laplacian algebras that are sub-algebras of polynomials that have two properties. First of all, the polynomial given by the distance squared from the origin, we want it to be in the algebra. And the second, we want the algebra to be invariant under the Laplacian operator, namely, right, for every polynomial in the algebra, we want the Laplacian, again, Laplacian just, the usual Laplacian in Euclidean space, to be also contained in the subalgebra. Okay, this being said, here is what essentially the theorem that I'm going to show comes from a collection of results that spans like a few years. The results are not the results in here do not correspond to specific papers, but they are kind of a mesh of all of those. And essentially, the results of all of these can be summarized in a few points. First of all, the moment you have a spherical manifold submetry, then the corresponding algebra of basic polynomials is a Laplacian algebra. So it has the two properties I was mentioning before. The second and important property is the following, that assigning to every manifold submetry the corresponding algebra induces an equivalence between the, it's actually a categorical equivalence. They're very simple categories, but nonetheless, these are two functors and that go from the geometric category of spherical manifold submetries to the category of Laplacian algebras. And if you go one direction, this is again the map that associates to every manifold submetry the corresponding algebra of basic polynomials. And if you go the other way around, what happens is that for any Laplacian algebra, well, you can think about the following. Any Laplacian algebra decomposes the sphere into level sets of the algebra. So what you can define an equivalence relation on the unit sphere by saying that 2 points x and y are equivalent if they cannot be distinguished by polynomials in A. So if f of x is equal to f of y for every polynomial A. And so what you can do is you can generate a map like this that just projects every point to its own equivalence class. This is like, if you go this way, there is no reason why you should believe that this is a manifold submetry. Why should the fibers be smooth, even less equidistant? But it turns out, and this is the big bulk of the theorem, that indeed what you have here is a manifold submetry, and again there is a 1-1 correspondence. This gives a way to turn problems in here into their algebraic equivalence, and the hope with this is to use an algebraic manipulations in here to pretty much maybe create something new that can produce new manifold submetries, for example. Or again, it really gives the hope that properties at the level of algebras can provide a really good information about and faithful information about the properties of the corresponding algebra, about the corresponding manifold submetries. Then there is a little bit more that can be said about this 1-1 correspondence. By the way, some people may have heard already this talk some time ago, and if you have, you may have seen the same thing happening, but in here, in the past, we had some extra assumption of maximality. I'm not going to explain what it is because it's not important for us because essentially the content of the latest of the latest result with Ricardo is that we got rid of this very technical and hard to understand condition, and now we have a much cleaner statement and much cleaner correspondence. Okay, so the third point in this theorem is that we can already start to see some correspondence. In here, as I was saying, these are somehow functors, and what it means is that we can take two manifold submetries, and if we can connect them by a submetry that makes the whole diagram commute, then what you get is that the two corresponding algebras are included into one another. It's not too hard. And then if you have a manifold submetry with connected fibers, this corresponds to an integrally closed Laplacian algebra at the algebra level. And then there is a last point that essentially says, let's see if I can say, well, again, says that at the level of manifold submetries, you have a covering theory, a theory of covering spaces with universal coverings. And the covering theory you have in here corresponds to Galois theory at the level of algebras, or rather at the level of their field of fractions of the algebras. And this is what it says here. Essentially, you can think of it in this way. Every element in this space has a universal cover. This is what it is saying. And in fact, the space itself is a quotient of the universal cover. So you can really think of this group gamma as the fundamental group of this element sigma. And in fact, if you think of gamma at the level of algebras, this gamma here corresponds to a group of automorphisms that fixes a subspace. The point is that in here you have Galois theory playing in the background. The fundamental group on one hand is essentially the Galois group of an extension on the other. Of all these, the most important thing is the fact that you have a 1-1 correspondence. And this has led already to some applications that actually find applications in invariant theory. The first application that I want to mention is this so-called inverse invariant theory. Maybe let me just let me mention what inverse invariant theory, what the inverse invariant theory problem is. Well, the inverse invariant theory asks if it is possible to characterize those algebras of polynomials that arise as the algebras of invariant polynomials for some group. So the question is characterize the algebras. This is more general, and this is just about algebras such that they can be written as algebras of G-invariant polynomials for some group G in GLV. This problem here was only solved by Mara Neusel for positive characteristics before this, and essentially what we could do is we can solve this problem for finite groups for finite groups in over the real numbers. So let me walk you through the statement. Essentially, it gives you exactly an if and only if condition for a polynomial to be written as the algebra of invariant polynomials for some finite group of isometries. And the if and only if statement is that this happens if and only if the algebra is Laplacian and it has cool dimensions, so the dimension of the ring is the same as the dimension of the vector space. What is, in my opinion, most interesting is that the statement is entirely algebraic. Both the hypothesis and the result is entirely algebraic. However, the way we prove it is necessarily to go through the whole metric machinery of manifold submetries, and then from there to produce the group gamma. So instead of directly applying the group theory or representation theory. By the way, I haven't said, but if you have questions, please do ask. Okay, so the second result is about a characterization of separating set. Now, this is a problem that appears in general in representation theory. What happens is the following: you have a group acting by isometries on a vector space, and you want to understand the full algebra of invariant polynomials. But what you can find easily is actually a set that separates the orbit, a separating set, which just means a set of polynomials that are like in large enough of a number that you can separate any two orbits. You can, for any two different orbits, you can find an element of the set that distinguishes the two orbits. Then you can, again, usually the separating sets are rather easy to find, but then it is hard to prove that they generate the whole algebra. And in here we give a good characterization. So whenever you define, say, B, the algebra generating by the separating set, if this set satisfies two conditions, that is to be invariant under two operations, then the algebra generated by the separating set is the whole algebra invariant. And although I do not have much time to discuss this, but this is a statement that generalizes something like the first fundamental theorem, Weil's first fundamental theorem for ON and SON and SUN. So this really has, this is very powerful, especially in situations like computational invariant theory, where you easily can produce these sets. And then it becomes a little bit more complicated to check if they're generating or not. I would like to finish. Yes.
Marco?
Yes.
Yes, a question. What would be an example of a Laplacian algebra which is not
That's a
related
good
to the
question.
key?
And I can give it to you very easily. I'm writing it here. An example. So it comes from the theory of Riemannian foliations mostly. So for example, take take a Clifford system. Seem to be so just a bunch of anti-commuting symmetric matrices that square to the identity. And if you have this, then you can generate the algebra A of RV that is generated by the quadratic polynomials that correspond to this polynomial, so generated by the polynomials Pix. So these are quadratic polynomials. Again, if you want, it is very easy to prove that it is Laplacian. Very, very easy. Somehow, this condition here gives you the whole thing. However, these pretty much none of these algebras here corresponds to an action. And as a matter of fact, if you have these, you can use these to compose. There is a composition operation that if you take any homogeneous polynomial, you can associate to that. Sorry, any homogeneous any group action. So the corresponding algebra. There is a composition operation that gives you an infinite family of non-homogeneous ones. So an infinite family of Laplacian algebras that do not come from group actions. So you do have, in fact, much more non-homogeneous ones than there are homogeneous.
Thanks.
Thank you for the question. I will finish with my questions here, and I will go very quickly. The first one is like, okay, we have a nice correspondence between spherical manifold submetries and Laplacian algebra, which is great. There is, so far, nothing is known about, there is no one-one correspondence or no characterization known for those Laplacian algebras that come from homogeneous manifold submetries. So the first question is like, is it possible to characterize those Laplacian algebras that come from homogeneous? So is it possible to characterize at the level of algebras which algebras come from homogeneous settings or not? This would be extremely useful in the case of homogeneous isoparametric foliations. And the second one, I will skip the last thing, so I will just finish with this. I think just, is it possible, to what extent we can understand the geometry of the base space in terms of like the diameter or the volume in terms of the algebra? I strongly believe that just the degrees of these polynomials, of the generators of this algebra, should give a lot of information, and from these would be possible to do things along the lines of a recent paper of Lichak, Gorozky, Mendes, and Lange, where they found a global lower bound for the diameter of orbit spaces of representations. Whenever you have a homogeneous manifold submetry coming from a group action, they can find the lower bound for the diameter. Can we do the same for group action? I am way over time, so I will stop here. Thank you very much.
Thank you. Thank you very nice. Thank you very much for the nice talk, Marco. Is there any question for Marco?
I have one question.
Go ahead.
Yeah. Marco, do you know what happens when you, I've already asked you this. Do you know what happens when you complexify a Laplacian algebra?
I don't. Well, you complexify and you get something, right? That is not what you get. I mean, like, sure, you complexify, you have polynomials, you take the level sets, would they correspond? Not sure. Definitely, they are not the orbit of the complexified group action. But one of the questions I wanted to ask is like, can we find the theory for the complexification that mimics the complexification of the group action? At the moment, there is nothing like this, and all the theory of like Kempf-Ness type theorems would be very, very interesting and useful to us to have in this context in terms of like algebras. There is nothing like this, and would be very interesting to have something like that.
Thanks.
Is there any
Marco?
other question?
Yes, I have one. Marco, concerning your second question,
Yes.
suppose gamma is a finite. Suppose gamma is finite and acting freely on the sphere. Okay, to be in the safe zone. So I think the corresponding Laplacian algebra determines the spectrum of the Laplacian on the quotient of the sphere, quotient the finite group, and the spectrum determines the volume of the quotient, right?
That is something we want to understand. So the Laplace, if you think about, right, the Laplacian algebra, essentially like the polynomials that generate it, like you can look at the Poincaré series, you have, you know, like how many elements in the, you can tell, let me just say, this Laplacian algebra is somehow determined by harmonic polynomials, and they correspond to the like eigenvalues, eigenfunctions of the Laplacian restricted to the sphere, which in some cases, like the ones you mentioned, you can think of them as just the eigenfunction of the Laplacian in the quotient space. And that, like, one of the reasons why I believe that the volume could be understood is because in there you have a by law that somehow, if you know how these eigenvalues grow, it can tell you what the volume is. I would like something like that I would like a by law for the general setting. The problem is when the group is not acting freely, the quotient is not even an orbital, so it really has singularities, and it has already been seen that you cannot hear those shapes. Like you have you can find the two isometric quotients from sphere, from different group actions that might be isometric, but with different. The point is that the Laplacian that you have downstairs does not correspond to the basic Laplacian upstairs. So it becomes hard to connect the two things. When the group acting is not finite, then the two Laplacians are not the same. Or they don't. It doesn't take Laplacian to Laplacian. There is an extra term that has to do with the mean curvature of the orbit, that kind of skews things, and things become a little bit more harder to understand.
Okay, but I guess when gamma is finite, doesn't matter if it acts freely or not, the volume must be preserved because of reason, right? These are good orbifolds, and the Laplacian works well in these cases. Exactly.
In those cases, I'm pretty sure that the usual by law can work, and you can get
Okay, thank you.
Thank you for the yes. That's nice observation.
Is there any other question or comments?
Yes, one more. So a Laplacian algebra is generated by the harmonic polynomials, right?
Well, the moment you add R, there is R squared.
Yeah.
You have R squared, and then all the other generators. So every Laplacian algebra is finitely generated. One generator is always R squared. The other ones, you can choose them to be harmonic.
Okay.
So I think we have time for one more question. So if there any other question?
So, yeah, okay. So what happens if you take like two submetries from spheres of different dimensions with isometric quotients? What happens with what's the relation between the algebras?
It depends. In the generality you mentioned, that we know nothing. there is a conjecture of Lichak that at least there is a way, like you can define a pullback that takes polynomials like one Laplacian algebra to Laplacian algebra. Although that map would not preserve the Laplacian. And this is all conjectural in this generality. If you add an extra assumption that this isometry of the quotients preserves the dimension of the strata, preserve the codimension of the strata, then we know from a work of mine with Alexandrino that you can find the pullback that commutes with the Laplacian. So in some cases, you have a very nice answer to your question. In some cases, we don't know nothing.
Thanks.
Well, thank you, Marco. We can thank again to him, and then we have a long break in the middle, so you can speak more about this. So thank you again, Marco.
Thank you.
So our next